Hello, everybody. As the first section of Calculus 4, we're going to talk about functions of two variables. The Calculus 4 is the subject to study multivariable functions. Particularly, we will develop the derivatives and integrals for variables more than two or three. And here we will mention a few concepts: domain and range and level curve related to a function with multivariables. And domain ranges are just common concept for every function, universal. And we've learned this from Calculus 1 uh, for single variable function. And this is just natural extension for multivariable calculus. So there's nothing new. But for the level curve, this is a concept only available for those functions of two variables or maybe three variables. So let's look at the definition. Here, we're going to talk about for a given function, what is domain and range. So we have a function, w equals f of x1, x2, xn. Then that means if you're given some values, x1, x2, xn, then it will determine w. Or in other words, the value of w depends on what value you give for x1, x2, xn. So for that reason, w is dependent variable and x1, x2, xn is independent variables. It's up to you. So the value assigned to the variables is independent variables or input variables. And w is called dependent variable or output variables. They are the same. And the scope of values x1, x2, xn's input variable is called domain, and the range is the set of all w values, output variable. And another concept is interior and boundary. And at the end, we will introduce what we mean by open and closed. So before we read this concept, we are going to look at an example, two examples. One is a region bounded by dashed line. Or another region, similar, but it was bounded by solid line. So by dashed line, we mean those boundary is not belong to the set. So what it means is you can think of your backyard, right? So in your house, suppose there is a tree at your boundary, at the boundary of the backyard. Some town defines this tree belongs to town, not your home. But if some town defines a boundary point or any tree at the boundary point belongs to your house. So this is difference. So for a dashed line, does not belong to the set. But solid line belong to the set. And in this case, just the first set is called open set, and second set is closed set. So how do we define these distinguish these two behaviors or these two sets from mathematical terminology? So the definition relates to what we mean by interior point and boundary point. So at an interior point, so suppose a point in a region is an interior point, then it is the center of the disk or positive radius that lies entirely in R. So if we look at here, this is interior point of your backyard because it can be covered by a small disk. This disk, you can decide the size of the disk, but it's a disk which entirely belongs to your backyard. This is also another interior point for the second set because you can always draw a circle, maybe very small, but doesn't matter. As long as there exists a circle, a disk covers the point, and the disk itself belongs to your backyard. But this point is not interior point because no matter how small disk you use to cover this point, you always have some part outside of your set and some part inside of your set. And again, because a disk covers part of disk belongs to your yard and your territory, and the other part is not. So this point is not interior point, and we call that as boundary point. And a region is open if it is consists of entirely of interior points, and a region is closed if it contains all its boundary points. So here, open set means does not include boundary. And this means include boundary. Another concept is boundedness um, or unboundedness. So a region in the plane is bounded if it lies inside the disk of finite radius. Otherwise, it's called unbounded. So what it means is, for example, there's a big region. You can imagine this is Massachusetts, the whole state. Um, it is big, but it is still bounded because I can cover it with even bigger disk. So this is bounded. But if we have a cone, something like imagine like this, then this is not bounded. We can imagine this cone extend to infinity. This is not bounded because any disk, no matter how big you draw, it doesn't cover the whole cone region, so unbounded. All right, let's look at an example. So this example involves all the concepts we have developed. So domain, range, and is it bounded, and is it open or closed? So the function we're going to study is square root of y minus x squared. First, let's look at domain. Whenever we have square root, we need to be careful that the expression inside cannot be negative. So that means the domain is x consists of two variables. Here, by the way, I want to clarify this is a function of two variables because there are two input variables, x and y, or independent variables, and outputs output variable is just z. So we count how many input variables, x and y, then two variable function. Now, because this is square root, we don't allow y minus x squared take negative numbers, so greater than or equal to 0. Or you can rewrite this as y greater than or equals x squared. For the range, again, it comes from square root. Square root of anything cannot be negative, so z is simply, we can formally write the output variable as z greater than or equals. Or another notation for this is including 0, the bracket means including this ending point to infinity, this interval. All right. Is it bounded? Is the domain bounded? Domain is given by x, y greater than or x squared. It's better to picture the region, what domain look like. So if we know that y equals x squared is parabola, then it is standard parabola moving, opening up, so moving up. And this parabola is a curve, but if we have inequality, then if we have inequality, then y is above this curve. Equality means a curve. So which means any point above this parabola belongs to the set or the domain. Then is it bounded? Obviously not. You cannot draw any circle which can bound the parabola, this region, because this parabola goes up forever. It never ends anywhere, so it's not bounded. The next one is the domain open or closed. And this is a good question. So if we look at the domain, this is the bound. First, we need to know if, so for openness or boundedness, we need to look at the boundary points if they are included or not in D. So is D open or closed? So for if if a domain if is given by inequality, in general, if the inequality is given by greater than or equal non-strict inequality, then this is closed. So what it means is, so D is the region y greater than or x squared, then the boundary points is x, y, which makes y equals x squared, which means this curve, every point on this curve is boundary. And because this is greater than or equal, so every boundary point is included. And so usually if D is given by x, y such that f x, y greater than or equal to 0, so if the inequality includes this, then it's closed. But on the other hand, if you have fxy strictly greater than zero, of course, we need some condition like f is continuing, but we're not talking about that much the details. So if fxy is strictly greater than zero, then it's open. So that's the general rule. So for example, here you can write this as xy and like y minus x squared greater than or equal to 0. And because this includes equality, so that means that includes boundary points. So one thing I want to conclude is from this example, maybe it's not directly related to this example, but in general, for the domain, if you have like square root or any even root expression, then the domain is greater than zero. So anything inside should be greater than zero. And if you have like fractions, right? So 1 over something, then this thing is not equal to 0. And if you have log of something, then this is strictly greater than 0. Level curves, this is new concept. Level curves and graph. So the set of points in the plane where a function fxy has a constant value f of xy equals c is called level curve of f. The set of all points xy fxy in space for xy in the domain of f is called graph of f. The graph of f is called the surface z equals f of xy. So what it means is, so we can think of a mountain surface. So a mountain surface usually like, for example, like this. We can model a mountain surface as f of xy, z equals f of xy, where z is height of mountain at given x, y coordinate. Then like the level curve, for example, 100 equals f of xy, then this is level curve. This is entire mountain or surface. Level curve means all those hiking trails which maintains the height sea level or the height of hundreds meters from the sea level. So this is, so suppose this is 100, so z equal 100 equals f of x. So this hiking trail, which at the level of constant level, 100, is a curve, not a surface. It's just a curve, and the surface is the whole mountain. And the surface is also called, in this case, it's called graph. So we look at this, yeah, this example. So it's about the level curve and graph. So we can look at, so the question involves with MATLAB. So the question is, the given function we have is this. Now, first, we want to use fsurf to look at the graph. So for this will be discussed. So those software applications will be discussed in LabWorks, our lab session. And there will be 3 homework problems due throughout the term. But here I will briefly mention how you use that. So we have lab work, lab session for details, but not here. Just for brief uh, instruction. So whenever we have this, we find out MATLAB online platform, and you probably need to open MATLAB. If you do not have account in MATLAB, you can sign up for that. It's free and open MATLAB online. It takes a few seconds. And we want to use fsurf, so the function to look at what kind of function it is. So here's the code. So first I need to assign two symbols for variables. So x and y. And then I will write down the function I'm looking for, 100 minus x squared minus y squared. Now I'm going to look at the graph. So to do that, we need first to put figure. So if we input figure, that gives an empty graph. Now on the empty graph, I can use fsurf to draw the graph. So if we look at here, yes, this just like a tent or a mountain. This is what it looked like. Now, so this is first problem. So the second one is level curve. Identify the level curve at 0, 51, 75. So what it means is, what is the hiking trail with zero level? So 0 equals 100 minus x squared minus y squared. In other words, if you're looking at zero level, then just replace the output as 0. Then this is x squared plus y squared equals 100. It's a circle with radius 10. This is a circle with radius 10 because this is 10 squared. And if you have 51, then 100 minus x squared minus y squared, it means this is 7 squared, 49. It is smaller circle. We can think of if this is mountain, this is zero level curve, and this is like 51 level curve. And for C, this is 75. Then again, we look at 75 level and put it as the output variable. And then it gives me an even smaller circle, maybe somewhere here. Plot its contour, level curves by F contour. So contour of a graph is those level curves with different levels, put them together. So if we look at here, so we need another figure. This is empty picture. And I do F contour, F. Then this is what it looked like. All right, this is for everything for the first section, and we're going to stop here.